All right, thank you for clicking on my talk. So before we start out, a bit of an inspirational story for graduate students is that I first met Karina at a conference and we were actually roommates, and she'd forgotten her swimsuit and I lent her mine, and so we became friends. And then we wrote a paper together. So the moral of the story is that you should talk to people at conferences. So in this conference, this means that you need to get on Zoom. So I did a bit of work on this, on Chabauty limits of the diagonal subgroup over SL and R, and then together with Karina Ciobotaru and Valette, we generalized it to SLN QP. So I need to tell you what I mean by a limit. So let G be a topological group. A sequence of closed subgroups H, N, and G limits to another subgroup H and G in the Chabauty topology if the following conditions are satisfied. So the first condition is that if I have an element of the limit group, I have some H and H, then there's a sequence of elements, Hn and Hn, that converges to it. So every element of the limit group has a sequence of elements that converges to it. And then conversely, if I start off with a sequence, and this sequence has some convergent subsequence that converges to some H, then H has to live in the limit. So the limit of any convergent subsequence has to live in the limit group. Okay, so the Chabauty topology is normally defined using a subbasis, but you can define it equivalently with convergence, which is what I've done for you, and I think it's easier to understand this way, and we're interested in limits for the purposes of this talk, so that's why I made that choice. And any space with the Chabauty topology is compact, so any sequence will have a limit. And the subgroup H and G limits under conjugacy to another subgroup L if I can find a sequence of conjugating elements Pn and G such that Pn HPn inverse converges to L in the sense of the definition above. So the Pn HPn inverse is now like my new Hn sequence. So let's see an example. So in SL2R, the diagonal is the group of diagonal matrices, as you see. And I've taken A to be positive so that it's connected. And I claim that this group has one limit up to conjugacy, which is the group of unipotent matrices. So according to the definition, I need to take some sequence of matrices and conjugate it and then prove that I actually get the limit that I wanted according to the definition. So for now on, I'm going to skip writing set builder notation because I think it's clunky. And when you see this matrix with A and 1 over A in it, you're meant to understand it as A ranges over all positive reals. So that's really representing a group there. I'm going to take this group and conjugate it by the sequence 1n01 as n goes to infinity. And when I conjugate, then I get what you see in the middle. And I claim that it converges to this unipotent group. So let's check the definition. I've put it here in tiny font to remind us. So the first part of the definition is that if I have an element in the limit group, then I need to find some sequence that converges to it. So picking an element in the limit group is the same thing as picking a real number x. All right, now I need to find something that converges to it. Okay, so n's going to infinity. So if I want n times 1 over a minus a to converge to a real number, it means that I need 1 over a minus a to go to 0. So that means I need a to go to 1. And then I can pick different sequences of a's going to 1 to get different real numbers x. So the first condition is satisfied. The second condition in the definition was that if I had a convergent subsequence, then the limit of that convergent subsequence belongs to the limit group. Okay, so if I have a convergent subsequence, since n's going to infinity, again by the same argument, it means that a has to go to 1. And so then in the upper right, I would get some real number. And the limit group is the set of all matrices of this form as x ranges over all real numbers. So the second condition is also satisfied. Now groups, like men, are best understood by their actions. So we should look at these groups acting on spaces. We're going to look at them acting on RP1. Now, RP1 is, you can think of it as the set of all lines through the origin, and you need to mod out by scaling. So if I let the diagonal group act on RP1, then I would see 2 fixed points, which correspond to the 2 eigenvectors. And now I can think of 1 and 0, 1, both as a sequence of matrices that I'm going to use to conjugate the diagonal group to the unipotent group. And I can also think of it as a sequence of projective transformations. And when it's a sequence of projective transformations, what it does to the geometry that's preserved by the diagonal group is it sends the first fixed point to itself, and it sends the second fixed point to n times the first fixed point plus the second one. So the second fixed point is collapsed onto the first one. And then in the limiting picture, you would see just one fixed point, which corresponds to the geometry preserved by n, where you see only one fixed point corresponding to the single generalized eigenvector. So the 1 and 0, 1 gives us a limit both on the level of groups as a sequence of conjugating matrices, and it gives us a limit on the level of the geometries preserved by the groups as a sequence of projective transformations. And this viewpoint will be useful to us throughout the talk. We'll want to go back and forth between groups and geometries that they act on. All right, so if we go up a dimension to SL3, there are 5 distinct conjugacy classes of subgroups in SL3, and each one is a limit of the diagonal. All right, so now wherever you see an A or a B, you should think about that as A or B ranging over any positive real number so that it's connected. A and B appear only in the diagonal. And then if you see an off-diagonal entry, which would be an S or a T, it can be any real number. So you see the diagonal group. And then there's a group which has a lower dimension diagonal. So now the diagonal only has dimension 1. And there's an off-diagonal entry. And this group F has a block form. The upper 2 by 2 block has all the diagonal entries matching. There's both A. And then there's the last block, which is 1 over A squared. And this ideal will come up later. And then we have 3 unipotent groups. And none of the unipotent groups are conjugate. So we said we wanted to think about groups and the geometries that they preserve. So C naturally preserves a projective triangle in RP2 because the vertices of the triangle correspond to the eigenvectors. And we can see each conjugacy limit of the diagonal as preserving a collapsed triangle. All right, so you see C, and now there's different ways that we can collapse this triangle. So for example, we might fix one of the points and suck in all of the points to it. So that would be like N2. Or we might stabilize the blue line and push the top point down onto the blue line. And that would be like N3. And there's several other things that you can do in between. And the idea is that you can go back and forth between the groups and the geometries. But we want to study QP. So we have to act on a different space. And SL2 QP acts on a P plus 1 regular tree. We can view the vertices of the tree as bases for QP squared, and we connect 2 vertices with an edge whenever we can do a change of basis that differs by a power of P. We can see the diagonal subgroup in this tree as the centralizer of the stabilizer of a bi-infinite geodesic in the tree. So what happens when we conjugate the diagonal group by 1 and 0, 1? Before we took n going to infinity. Now we need to take the p-adic valuation of n going to infinity. And when we do that, we would see the same algebraic computation, and the limit would be, again, the unipotent group. But we want to see it in the tree. So C is the stabilizer of a bi-infinite geodesic. And this bi-infinite geodesic has a base point. And what does 1 and 0, 1 do? It pushes it off of the base point, pushes this infinite geodesic off the base point, and it pushes it towards the ends of the tree. And as you get pushed out farther and farther into the tree, eventually you would converge to one end. And this limit group n preserves exactly this end of the tree. So now we want to take this idea and go up a dimension to SL3QP, where we have to act on a space that's a bit more complicated. And in this case, we're going to act on an analog of the tree a dimension higher. And in general, these are called buildings. So here I've tried to draw the part of the building for SL3QP. So you start out with R2 that's tiled by equilateral triangles. And then on each infinite geodesic, we're going to glue in p+1 copies of the same tiled R2. So remember, in a tree, at each vertex, you glued in p+1 edges. Now, at each line, we're going to glue in another p+1 copies of R2. So then on the right, I've tried to draw what this would look like for you, or at least a piece of it. And you get this very big, non-positively curved space in the end. And SL3QP has a highly symmetric action on this space. So if I pick a triangle, say I color it blue, and then I can pick a side of the blue triangle, there is an element of SL3QP that sends the blue triangle and its side to any other triangle with a side that I've chosen. So it's a very symmetric space with a very symmetric action of SL3QP. And C is the centralizer of the stabilizer of one of these infinite tiled R2s. And we need to understand how to go to infinity in this space. And that's how we're going to see the limits of C geometrically, is by going out to infinity in the building. And when we go out to infinity, what we see is a bunch of complexes like this that are glued together. And that's called the spherical building at infinity. So we're going to see a bunch of hexagons that are glued together somehow. And each hexagon is going to play the same role as the R2 that was tiled with equilateral triangles. So here I've drawn a portion of the spherical building at infinity. I've drawn the link of one vertex in the building for SL3Q2. And it just so happens that the link of a vertex in the building for SL3Q2 is also the building for SL3F2. F2, the field with two elements. And what I've drawn here is the Heawood graph. It's a very famous graph worth studying in its own right. It's the incidence graph of the Fano plane. There are 14 vertices. It's bipartite, and the shortest cycle is length 6. So it's made up of a bunch of hexagons that are glued together. Now, the bipartiteness corresponds to two different colors of vertices, which represent the different ways that we can go to infinity. So if we look at the roots, we could stabilize a root or an eigenvector, and we could collapse everything onto it, and that would be like one of the red vertices. Or alternatively, we might stabilize the space spanned by two of the roots and collapse into that, and that would be like one of the blue vertices. Or we could stabilize a flag of one root and then the space spanned by that root and another, and that would be like an edge between a red and a blue vertex. So all these different vertices and the edges between them keep track of the different directions in which we can go to infinity, and there are limit groups that are attached to each of these edges and vertices. So one of the nice things that we're able to do is to enumerate limits in low dimensions. So I defined curly qk to be qp star mod qp star to the kth power. It's the number of kth root classes. So for example, in R, I either have a positive number, which is a square, or I have a negative number, which is -1 times a square. So in R, there are two square classes. In QP, there can be many kth root classes for a given k, and you can compute them. This is pretty standard in number theory. So I've made a little chart to enumerate the number of limits in low dimensions. So when n equals 2, we saw that both over R and over QP, there are two limits up to conjugacy. When n equals 3, we saw that over R, there are 5 limits up to conjugacy. And over QP, there are 4 plus the number of cube root classes over QP. And I'll show you why it's cube root classes in a second. And then when n equals 4, there are 14 limits up to conjugacy over R. And over QP, we have some bounds that depend on either the number of 4th root classes or 8th root classes. So why do we see more limits over QP? So for example, when n equals 3, I've drawn a group for you. So here, S and T could be any real or p-adic number, and alpha is some fixed real or p-adic number. Over R, it so happens that all of these groups are conjugate for any value of alpha. But over QP, one of these groups is conjugate to another if and only if alpha and beta are in the same cube root class. So that's why we start to see these kth roots popping up. In both SL7R and SL7QP, there are infinitely many non-conjugate limits of the diagonal group, and also for all n bigger than or equal to 7. So there's a combinatorial explosion that happens as soon as n equals 7, and we're not quite sure why. N equals 5 and 6 are open. So for n equals 5, we know that there are still finitely many limits up to conjugacy, but we haven't written them down, and it gets large and it gets to be a bit of a headache. For n equals 6, it's unknown whether there are finitely many or infinitely many limits up to conjugacy. So there's an open question for you if you're looking for something to do. So there are a few difficulties that we had to overcome when we went from R to QP. So the first one is that in general, the exponential map is functorial only to the germ. The germ is a very tiny neighborhood of the identity. When you're doing things over the reals, it's often very convenient to go back and forth between Lie algebras and Lie groups. And the exponential map is a functor that does this, because what's happening in a neighborhood of the identity in the Lie group is actually enough information to tell us what's happening in the group. And so we can go back and forth. But the problem is that QP is totally disconnected. So the germ is too small to actually give us enough information to go between Lie groups and Lie algebras. So what we had to do is we had to build our own exponential map so that we could also pass between groups and algebras. Another problem that we had to overcome is how to reduce from the algebraic closure back down to the field. So if you're working over R and you go up to C, then the Galois group of C over R is just Z mod 2Z. So you don't have a lot of work to do if you want to reduce back from C to R. If you go up to the algebraic closure of QP, then you would get a Galois group, which is an infinite profinite group. So you have to do a lot more work if you're going back down from the algebraic closure to QP to figure out what is the same and what isn't. Another problem is that if a real group is elliptic, then it only has one in the diagonal. In the QP case, it's harder to show that. In the QP case, you could have elements on the diagonal which are in ZP, and your element can be elliptic. So we had to work hard to kill these ZP elements in the diagonal and show that our unipotent groups are, well, almost unipotent. So they either have one or they might have a root of unity on the diagonal. And we had to build this exponential map to kill these ZP elements on the diagonal. And to do all this, we used a building for SLNQP, which is an analog of what we saw in lower dimensions. So you can think of SLNQP mod SLNZP as an analog for the symmetric space SLNR mod SON. So somehow SLNZP is like a good maximal compact that we want to quotient out by. Then we have to add a little bit of extra structure so that it acts like a symmetric space. So given a locally finite thick affine building, let F be a facet in the spherical building at infinity. So locally finite means that there are finitely many things glued together at each place. Thick means there's at least 3 things glued together. So given a facet, we can define a parabolic subgroup, which is the group of elements that stabilize that facet in the spherical building at infinity. And recall that a parabolic subgroup has a Levy decomposition. So for SL, parabolic subgroups have this block form. And then the Levy decomposition decomposes into the Levy factor, which is the diagonal blocks, and the unipotent radical, which is the stuff that's not in the diagonal blocks. And then this is what we were able to show. So if you start with the diagonal group and you have some limit of the diagonal group, then if L contains only elliptic elements, then L is contained in the unipotent radical of a parabolic stabilizing a facet in the spherical building at infinity. And L might have roots of unity on the diagonal. So this is very nice because it organizes the limits in a way that we weren't able to do over R. Over R, we didn't know which limits limited to other limits. But over QP, this question is answered for us by the combinatorics of the building. The building is organized because vertices are contained in edges, edges are contained in triangles, etc. And you can see that one limit is going to limit to another if and only if the facets are contained in each other. So the geometry of the building organizes all the limits for us in a very nice way. And we can see them all in the building at infinity because they're all attached to a facet. So that's what happens if the limit contains only elliptic elements. Well, if you don't contain only elliptic elements, then you contain some hyperbolic elements. And if L contains hyperbolic elements, then a flat torus theorem tells us that L stabilizes a flat. So L stabilizes a subspace that looks like Euclidean space. And then L has a block diagonal form where all the diagonal entries within each block match. And I think we saw an example of this before. So we've been able to understand all of the limits in this very, very precise way using the geometry of the building. Thank you for listening.